Hello maths fans, Dr Tom Crawford here at the University of Oxford, and today we're learning how to calculate the inverse of a matrix using elementary row operations. I'll explain each step as we go, but to really get the most out of this video, make sure you watch the first one in the linear algebra series, which explains what elementary row operations are and how they work. In the video description, you will find lots of sample exercises and example videos courtesy of ProPrep, an online resource that provides customized tutorials for students looking to improve their skills in STEM-based subjects. You can access the videos by signing up for a free trial using the link below. To start, we're going to think about what it actually means to calculate the inverse of a matrix. So let's suppose I have a matrix denoted by A, then the inverse, which we denote A minus 1, will multiply with A to give us the identity. And the identity matrix, remember, is a square matrix where all of the diagonal entries are 1s and all of the other entries in the matrix are 0s. We will be looking at a concrete example shortly. Now you'll hopefully remember from the first video on elementary row operations that when applying EROs to the coefficient matrix when trying to solve a system of linear equations, we wanted to reduce the coefficient matrix to the identity. Now there is a reason that the identity matrix also appears here when we're calculating inverses. When we apply EROs to a matrix and turn it into the identity, this is actually telling us what we need to do to find the matrix inverse. And this makes sense because multiplying a matrix by its inverse gives you the identity. So we just need to work out how do we represent the EROs that we're going to apply here. How do we represent these as a matrix, and then hopefully all of those matrices, which will be applied to A to turn it into the identity, that will actually tell us what we need to do to get A inverse, because this is doing exactly the same thing. Multiplying by an inverse also turns A into the identity. Fortunately, it turns out this isn't too tricky. The action of an ERO on the matrix A is in fact the same as pre-multiplying our matrix A by something which is called an elementary matrix. Now, the elementary matrix is in fact just the n by n identity, where n corresponds to the size of A, where to the identity we've applied the elementary row operation that we want to do to our matrix A. So let's look at a concrete example. Suppose my matrix A is, let's have 2, 1, 1, 4. So it's a simple 2 by 2 matrix with all positive entries. And now what I want to do is swap row 1 with row 2. So I know that the answer should be, and I'll put a question mark here because we're going to check this, but I know the answer should be the same matrix with those two rows swapped. So 1, 4, 2, 1. Now the theory says to pre-multiply by an elementary matrix, which is the identity, with this ERO applied. So what that is going to be is the 2 by 2 identity would be 1, 0, 0, 1. Swap the rows. So now it's 0, 1, 1, 0. So this is the 2 by 2 identity, and what we've done is we've swapped R1 and R2. So it's just the identity matrix with the ERO we want to do, whatever that may be, within the 3 that are allowed, applied to the identity. Now let's check that multiplying these two together does indeed give us the matrix A with 2 rows swapped. Now remember, when doing matrix multiplication, we want to know the first entry here. So this is the first row and the first column of our output matrix. So we take the first row and multiply by the first column. So it's 0 times 2 plus 1 times 1, so that's 1 when I add them together. Now the first row, second column, so first row here, second column, 0 times 1 is 0, plus 1 times 4. Then we do second row, first column, 1 times 2 plus 0. And then second row, second column, 1 times 1 plus 4. So multiplying the two matrices together, which is our elementary matrix that represents the ERO, multiplied by our matrix A, it's exactly what we've done, and we get 1, 4, 2, 1, which is indeed, I can put a tick here now, maybe a smiley face. It's exactly what we wanted to happen. We have outputted our matrix A with the two rows swapped. So doing the ERO of swapping row 1 and row 2, we've shown here was the same as pre-multiplying by this elementary matrix, which is the identity with row 1 and row 2 swapped. So ultimately, what this means is that if we can keep track of the EROs that we are using to turn our starting matrix A into the identity, and then we do the exact same EROs to the identity matrix, we will get the inverse. So just to repeat that for clarification, if we can keep track of the EROs that we need to turn any matrix A, and we have this example here, if we keep track of the EROs to turn this matrix into the identity, then if we do the exact same EROs to the identity matrix, that will in fact give us the inverse. So let's try it out. We're going to start with a simple 2 by 2 matrix, so let's use the one that we were just looking at. So my matrix A is equal to, we had 2, 1, 1, 4. Now, the first step here is to actually create something called the augmented matrix. And what that just means is we kind of add an additional matrix next to our starting matrix A, which is just going to be the 2 by 2 identity. Now the reason we do this is that, remember, in order to find the inverse of A, we need to keep track of the elementary row operations required to turn this into the identity and do those exact same EROs to the 2 by 2 identity. So if we write the matrix like this in the augmented form, so this gives us a really nice way to keep track of the EROs that are being applied. Because what we're going to do is apply EROs to turn our matrix A into the identity. So we want this to become the 2 by 2 identity, which of course is 1, 0, 0, 1. But given the augmented matrix form, we can just apply the same EROs to this part of the matrix, which is the 2 by 2 identity, and this will eventually become our inverse A minus 1. So apply EROs, turn this into the identity. Once this is the identity, whatever is left here, having applied the same elementary row operations, that is going to be your inverse. So let's actually do the calculation. We want to turn this first part of our matrix into the identity. Now remember, the starting point was to rescale the first row because we want our leading entry to be a 1 because that's what it needs to be in the identity. So our first ERO, and I will keep a list of these even though I'm going to just be applying them and rubbing out what's happening in our matrix. So our first ERO is going to be to do a half of row 1. So we're just going to, that's going to become 1. This is multiplied by half. This becomes a half. And then 0 times a half is, of course, still 0. Now we need to make this entry a 0. So what we need to do as our second ERO is going to be row 2 minus row 1. So we do 1 minus 1 is 0, 4 minus a half. So that's actually going to give me 3.5, which is 7 divided by 2 as a fraction. We need to then, remember, do it to the right-hand side. So 0, and then we're doing minus row 1, so that becomes minus a half, and then 1 minus 0 is still 1. Next, we want to make this entry, the 2 by 2, 2, 2 entry, we want to make this a 1. So that means multiplying row 2 by, that's going to be 2 over 7. So we need to do 2/7 times row 2. So 0 times 2/7 is 0. 7 over 2 times 2 over 7, that was designed to give us exactly 1. 2/7 here, so we've got a minus. 2 divided by 2, that's 1, so that's going to be now a minus 1/7. We multiply that one. And then 1 times 2/7, well, that's just 2/7. Okay, looking good so far. Now we just have one entry left, which is this one in the top, the 1, 2 entry, first row, second column. So what we do there for our fourth and hopefully final elementary row operation is we are going to subtract off a half of the second row. So row 1 minus a half of row 2. So we have 1 minus a half times 0, that's still 1. A half minus a half, so that becomes 0. And now we have our 2 by 2 identity, which is very promising. We also, of course, have to remember to do it to the right-hand side matrix. So we want a half minus a half times minus 1/7. So that's minus a half plus, and then we've got 1 over 7. Minus a half times minus 1/7 becomes plus a 14th. So it's a half plus a 14th. So that's 7 out of 14 plus 1. So that's 8 out of 14, which I believe is going to be 4 out of 7. Okay, so I think that's 4/7 when we do that. And then we have 0 minus a half times 2/7, so that's minus a 7th. So that should be minus 1/7. And now we've finished. We have performed these 4 elementary row operations to our 2 by 2 matrix A. It has been reduced to the identity matrix, and we've also applied the exact same, in the same order, 4 elementary row operations to the 2 by 2 identity. And then the theory tells us this should, and I'll write a question mark because we're going to check this should be A inverse. And of course we can check if this is correct by simply doing A multiplied by A inverse and see if we get the identity. So let's do it over here. We started with our matrix A, which was 2, 1, 1, 4. And then through our calculation using EROs, I'm telling you that the theory gives us that this is the inverse. So if we multiply this matrix by 4/7 minus 1 over 7 minus 1 over 7 and then 2/7. And this should hopefully, if we've done it correctly, give us the identity. So first row, first column. 2 times 4/7 is 8/7 minus 1/7. That gives me 7 over 7, which is indeed 1. Now, first row, second column. Minus 2/7 plus 2/7, so that's 0. Looking good. Second row, first column. 4/7 minus 4/7, that's also 0. And then second row, second column, minus 1/7 plus 8/7 gives me 7/7, which again is 1. So we get a tick, and again, we get a smiley face, because the inverse we've calculated here by just applying the same EROs, these 4, to the identity, that's given us A inverse, and we've checked, and it does work. A times A inverse, where this is A inverse, does indeed give us the identity. Our last example was a simple 2 by 2 matrix. However, the exact same method will work on any n by n square matrix. So just to be sure, let's check for a 4 by 4. So our matrix A is going to be equal to the following. Now, as before, our first step is to form the augmented matrix, which means adding the relevant size identity next to our starting matrix A. So the identity matrix, as always, zeros everywhere except the diagonal, which contains 1s. Now to find our inverse, remember we just apply EROs to turn the left-hand side into the identity, and we keep track of those EROs and make sure we also apply them to the right-hand side, i.e. the identity, and whatever is left here, when the left is the identity, whatever's left over here, that's going to be our A inverse, that's going to be our inverse matrix. Looking at our matrix A, we have a nice leading 1, exactly where we want it. However, we need to get rid of these 2. So the first EROs we're going to do is simply to do row 2 minus row 1, and I'll write a couple of them together to help speed this up. We're also going to do row 3 minus row 1. Okay, so after our first combination of EROs, we have a nice leading column, and our matrix looks like this. Now the second lot, we're going to concentrate on this second column. Now what I'm going to do here is use the 1 that we have, which is in the position we want it to be, in row 2, and I'm then just going to add multiples of row 2 to row 1, row 2, and row 3 to get those zeros. So what we want to do now is row 1, we need to add row 2. That'll work. Then we need to do row 3 needs to be minus row 2. And our third one, we're going to need to do row 4, also minus row 2. All right, so we've done that one, and we've done that one. Next, we look at the third column. So again, we have the 1 that we want. So we just need to add multiples for the top 2 and subtract a couple for the third one. So our third set of EROs is going to mean to do row 1 plus row 3, row 2 plus row 3, and then we also want row 4 minus 2 lots of row 3. 2 lots of row 3. Now, we're very close here, just this last column. So I'm going to make things a little simpler, and I'm going to do my fourth ERO is just going to be 1/3 times row 4, just to get this 3 to become a 1. So we can get rid of the 3 and get a 1. This becomes a third, minus 2/3, and 1/3. And then our final set of EROs is just to get these to all become 0. So I just need to add row 4 to row 1, row 2, and row 3, and then we've got the identity. So I need to do row 1 plus row 4, row 2 plus row 4, and row 3 plus row 4. And fingers crossed, that will give me the identity. So this should now be equal to A inverse. I've applied 5 sets of EROs to reduce the starting matrix A to the 4x4 identity, and I've applied the exact same elementary row operations to the identity to get this, which I believe is going to be A inverse, and I will just check that now to be super certain. So here is my starting matrix A. This is A inverse, where what I've done is, because there's this common factor of dividing by 3 or 1/3 in the whole matrix, I've just pulled it outside the front over here. So this is A inverse. Let's multiply them together and we should get the identity. So this is going to equal 1/3 times, and hopefully this will now be 3 lots of the identity. So let's check. First row, first column. So 1 times 1, that's 1, plus 2, plus 0, plus 0. So that's 3. Excellent. First row, second column, that's 1, minus 1, that's 0, plus 0, that's 0. Excellent. First row, third column, that's 1, minus 1, that's 0. And first row, last column is also 0. Okay, so the first row looks good. Second row, first column. So that is now 1, nothing, minus 1. So that's a 0. Okay, good. Second row, second column, minus 1 plus 2, and then that's a 0. So that's going to be a 3. Perfect. Second row, second, 1, 0, minus 1. Good, that's a 0. Second row and last column is going to be 1, minus 1. Yeah, 0. Okay, so far so good. Third row, first column, got a 1 and then a minus 1, so that's a 0. Then we've got second column, we pick out the 1 and the minus 1, it's also a 0. Third column, we pick out a 1 minus plus 2, beautiful, that's a 3. And then this one times the last one, 1 and a minus 1 is also 0. Nearly there. And then the fourth row times the first column. So we get a minus 2 plus a 1 plus a 1, so that's a 0. And we get this one times this one, so that's a 1 minus 2 plus 1, that's also 0. And then we get this one and this one, which is a 1 plus a 1 minus a 2, that's also 0. And hopefully we're going to get 3. Perfect, exactly what we want. Amazing. So this is indeed the inverse with the 1/3 multiplying it through. So this is our inverse matrix. We double checked our original A times the inverse for a 4x4 matrix does indeed give us the identity. If you want to practice this technique for yourself, then do check out the links to the video exercises and solutions from ProPrep, which can all be found in the video description below. There are plenty of exercises for matrices of all different shapes and sizes, which will keep you busy for hours on end. Now, there is one final thing to be aware of when using this method of EROs to solve for a matrix inverse. And that's that not every matrix will have an inverse. Sometimes A minus 1 will not exist. But we don't actually need to worry, because this method will tell you exactly when that is the case. There is a sign to look out for which indicates that the inverse does not exist. And this sign is actually the same as what we saw in the first video when we were looking at ERO's elementary row operations and using them to solve a system of linear equations. Now, in the first video, we said a system of linear equations does not have a solution if the ERO form contains a 0 row. And the exact same thing is true here. So if, for example, I had got to this point, and in fact, this fourth row was all 0, so I'm trying to reduce my matrix A down to the identity, but I get to a point where I have a 0 row, something like this. Now, what this tells us in this context is the original matrix A does not have an inverse. So you proceed with the method exactly as before, nothing changes. You try to reduce your matrix A to the identity, you apply the same EROs to the right-hand side, the identity, to get potentially the inverse. However, if you get a 0 row on the left-hand side, that tells you you cannot reduce your original matrix to the identity, and what that means here is the inverse does not exist. There are some further video exercises courtesy of ProPrep which look at when matrices do and do not have an inverse. So I highly recommend checking those out too, just to make sure you've really got the hang of the elementary row operation approach to matrix inverses. As usual, all the relevant links are in the video description. Thank you everyone for watching. Please do remember to subscribe if you've enjoyed the video, and I'll see you all soon. Take care.